Greetings and welcome to Distiller. In the previous class, we discussed about different ways to represent a chemical process. So whenever we are representing a chemical process, we represent it in the form of diagram so that people are able to understand what is going on in the process. So there are three diagrams that are used for representing a chemical process. The first diagram is nothing but a block diagram. In the block diagram, we have different units connected in the form of blocks to explain the order in which the process is taking place. All right. The second type of diagram was a process flow diagram. In the process flow diagram, we give more detailed information. We use symbols for different equipments used. And the third diagram was the piping and instrumentation diagram, in which every detail is mentioned. For example, equipment name, equipment dimensions, equipment material made, and different other information like valves, pipings, pumps, etc. All right, so we discussed about this, and then we discussed how to make a block diagram, in which we discussed that in order to make a block diagram, we first of all need to identify the unit operations that are taking place. Then we need to arrange them in a particular order, in the order in which it is mentioned in the process description. And finally, we have to connect each and every block using arrows so that we get that what is going on in the process. Now, today, we are again going to start with material balance in a bit more detail. All right. So there are two types of processes, batch process and continuous process. So when we talk about a batch process is a process that involves processing of materials in a batch mode. So this implies that all materials to be processed are fed to the unit at once, and then the processing is allowed. So suppose if you want a chemical reaction to take place in a reactor. All right. So this is a particular reaction that has to take place in a reactor. So what will I do in the reactor? In my reactor, I'll feed or I'll put all my A at once. All my reactor, I'll fill with A at once. All right. And then after, suppose if I do this at time t equals to 0, then after some time, let's say after t seconds, or let's say after t1 minutes. Okay. So after t1 minutes, I'll finally extract whatever is there inside this particular reactor. So between t equals to 0 and t equals to t1, whatever conversion has taken place from A to B, that will be obtained after t1 minutes. So this is my batch process. So once the materials are allowed to process for a given amount of time, they will be withdrawn from the unit. This process is also known as unsteady state process. So this means that the composition of the material being processed at a given point within a unit will change with time. All right. So for example, let's take the same example. So let's say I'm having this reactor that I have filled with A. All right. I have this reactor that I have filled with A. All right. Now this is at time t equals to 0, where 100% of it is A. All right. Let's say I check this after some time. Let's say after 10 minutes. So if I check after 10 minutes, then you'll realize that, let's say we are taking, for reference, we are taking this point, and we are seeing that what is the composition that has changed at this point. So after 10 minutes, you will realize that at this particular point inside the reactor, the composition has changed. Because after 10 minutes, of course, some amount of A would have converted to B. So that amount of B, let's say 10% conversion has taken place. So we'll have 90% A and 10% B. Let's say I do that after 20 minutes. I check again after 20 minutes. So I'll get a different composition. So you'll see that if you take time and if you take concentration, then with time, concentration would vary. with time, concentration would vary at this particular point of reference. All right, this particular point of reference. All right, POR, point of reference. All right, so at this particular point of reference, the concentration would vary with time. Hence, this is a unsteady process, unsteady state process. All right. Then when we come to continuous process, so in a continuous process, processing takes place continuously. The material is fed continuously at a given rate and it is taken out at a given rate. So for example, if this is my unit, then I'll be feeding A from this side of the unit and I'll be extracting whatever has been converted. Let's say 90% of A has converted. So we'll get 90% B and 10% A. All right. So whatever A we have, we'll get it on this side. All right. So when we do that, when we do that, so this type of a process is known as a continuous process. It is fed continuously and it is extracted or taken out continuously. All right. At the start, it is an unsteady state process, but eventually, as the system achieves equilibrium, the process becomes at steady state. All right. So this means that at a given point inside the unit, for example, let me take this particular point of reference. I'm taking this particular point of reference. All right. So at this particular point of reference, let's say at time t equals to 0, I'll get, let's say 20% B and 80% A. All right. So this is going to remain throughout at time t equals to 0, at time t equals to 10, 20. This is going to be the same 20 plus 80, 20 plus 80, 20 plus 80. 20 plus 80 as in 20% A, 20% B and 80% A. All right. So as you can see, the concentration, it is not varying with time. All right. Concentration is not varying with time or composition is not varying with time. So that is why it is a steady state process. So if we also try to explain it graphically, then let me tell you, if we have an unsteady state process, with composition versus time, all right, at a given, this is again the graph for at a given point, all right, at a given point within the unit, that I'm calling it as the point of reference. All right, so at the point of reference, if I vary concentration, if I see the variation of concentration with time, so it will vary. So depending on what concentration we are measuring or what composition we are measuring, it's going to vary anyhow. All right, so something like this you'll observe. So you can see at time t equals to 0, the concentration was something else. At time t equals to t1, the concentration is something else. And at time t equals to t2, it is something else. So this kind of a process is an unsteady state process. All right, unsteady state process. All right. At the same time, let's say if we take for a steady state process, then as I discussed with you, at the point of reference, whatever the point of reference may be, the concentration is going to stay the same irrespective of time. So if it is 20% A, 80% B, it's going to be 20% A, 80% B throughout. All right. So the concentration is going to stay constant. All right. So it's going to be a horizontal line, a straight horizontal line. All right. So at any point of time, if you observe the concentration, it is going to be uniform. All right. It is going to be the same. All right. So this type of a process is known as steady state process. All right. So from here, if you see the slope of this graph, concentration versus time graph, then if we have a y versus x graph, if we have a y versus x curve, then what is the slope of this curve? It's obviously dy by dx. So here, if you see the slope dc by dt, then it's not going to be 0. It may be negative or positive depending on what unit operation is taking place, right? But over here in at steady state, you can see it is horizontal. That means dc by dt is equal to 0. Hence, this is a very important result. This is a very important result for a steady state process. dc by dt is always equal to 0. There is no variation. If we take, let's say we take any property n, we take any property n, or yeah, all right, for n. So n would not vary with time. dn by dt is going to be equal to 0 for steady state process always. All right, irrespective of the type of the process, irrespective of the unit operation. If it is a steady state process, the moment you see the word steady state, you have to make sure that you're going to say that d property by dt is going to be equal to 0. All right, suppose if it is a heat transfer process, then the process variable in that case is temperature. The temperature changes, right? So if heat transfer is taking place at steady state, then you'll get dt by dt equals to 0. All right. If mass transfer is taking place, then in mass transfer, the process variable is concentration. All right. So you'll get dc by dt equals to 0. All right. So this is quite important. You must keep this in mind that whenever a process is at steady state, then at a given point of time, its property does not vary. Its property does not vary with respect to time. Its property is always constant at a particular point within the system. All right. So that is about an unsteady state and a steady state process. So a batch process is an unsteady state process, while a continuous process is eventually it goes to steady state. In the start, it's unsteady state process, but eventually it goes to the it achieves equilibrium and it becomes steady state. So graphically, if you represent this thing, so it would be something like this. So initially up till here, initially in the beginning, it was unsteady, and after that it has become steady state. All right. So something like this can be observed. Why I have introduced you to this thing? Because further, when we'll study more subjects, we'll be dealing with these things a lot. So at that time, you should not be confused about steady and unsteady state process. Then we come to two very important concepts: control volume concept and control mass concept. All right, control volume and control mass. So let's understand what is control volume and what is control mass. Fine. So whenever we have a system, what is a system? A system is any particular space on which, or you can say any particular part of the universe on which our calculations are based. All right. Suppose if you want to study about boiling of water, then in that case, water is your system because our calculations will be based on water. All right. So system is a part of the universe that is our that we need to perform our calculations on, or that we need to analyze. All right. So whenever we are trying to analyze a system, then there can be two analysis for the same. Okay. Whenever we are performing analysis of a system, then there are two ways in which it can be analyzed. The first way is using a control mass concept. All right. In control mass concept, what we are going to do, we are going to make sure that the mass is fixed. We are going to make sure that mass, the amount of matter, is fixed. All right. So let's say, let's for example take a gas. Let's for example take a gas that is flowing through a pipeline. All right. A gas that is flowing through a pipeline. Now let's say in this gas, I'm selecting these three molecules. All right. These three molecules I'm selecting in this gas, and these three molecules are a part of my control mass approach. All right. They are a part of my control mass approach. Now let's say wherever these three molecules are going to go. We are going to track these three molecules and we are going to deal with our calculations. All right. So suppose if further, if this particular pipe, it, let's say, enlarges, all right, it enlarges in this manner, then obviously these three molecules are going to spread out. So one molecule might come here, another might come here, and another might come here. So then our control mass would become this. All right, our control mass is going to become this. So if we call this, the first one as CM1 and second one as CM2, then let me tell you, CM1 is CM2. Both are the same. All right. Because we are taking both to be the same, because mass of CM1 is same as mass of CM2. Because we are tracking only these three molecules, right? We are tracking only these three molecules. So these three, wherever these three molecules go, they are a part of our system. All right. They are a part of our analysis. All right. So in this entire universe, wherever these three molecules will be located, that would be our system. All right. So if they are in this much small area, then also, or this much small volume, then also it's a part of our system. When it is in such a large volume, then also it is a part of our system. So here you can see that our mass is fixed. Our mass is fixed. Our volume is variable. All right. Our volume is variable. All right. But our mass is fixed. Okay. Our mass is fixed. So this kind of an approach is known as a control mass approach. All right. So in a control mass approach, if you take a particular control mass, then suppose if you are making an assumption that this particular control mass has a mass of m, then as long as you are going to track that control mass, this m is going to go with us. All right, this m is going to go with us. Clear? However, we rarely use this control mass approach because it's quite impractical, right? It's quite impractical. It's not possible to track three molecules, or it's not possible to track a set of molecules, right? So that is why the more commonly used approach for our calculations is a control volume approach. All right, a control volume approach. So what happens in a control volume approach? In a control volume approach, just like from the name, you can get that a control volume approach keeps volume constant. All right, volume is fixed. So suppose if let's take the same pipeline. Just a minute. So let's take the same pipeline, and again I'm going to track my system. All right. So now if we take this track, if we take this particular pipeline, then in the control volume system, in the control volume approach, we are going to track this fixed volume. We are going to track this fixed volume. So no matter how many molecules come in, go out, it doesn't matter. No matter how many molecules are inside this space, doesn't matter. All right. What matters is that the space should be constant. All right. The space should be constant. All right. So in a control mass approach, in a control volume approach, we take a particular space in the universe, and we only track that space. So if molecules are coming in, so let's say in the beginning, these are the molecules that have come in. After some time, these molecules have gone out. After some time, these molecules have gone out, and some other molecules have come in. All right, some other molecules have come in. All right, and these other molecules may be like over here, these are 4 molecules. Those might be 5 or 6 molecules, right? So the mass is varying, right? Mass is varying, but the volume, the space, it is constant. So keep in mind, whenever we are using a control volume approach, Mass might vary, but the volume is fixed. Whenever we are using a control mass approach, mass is always fixed and volume might vary. All right. However, at steady state, when we generally take steady state operations, then usually it happens that a control volume approach is reduced to a control mass approach. The reason being that at steady state, since all the flow becomes uniform, right? The flow becomes uniform. So suppose if 4 molecules are coming in, then 4 molecules will come in at every point of time. The flow becomes quite uniform. Therefore, it approximately gets reduced to control mass approach. All right, both become the same. And also, when we take a practical system, then we don't take such a small control volume where there are only 4 or 5 molecules. In that case, we take a very large piece of volume, right? So in that case, we are going to say that the change in the number of molecules, let's say 1 or 2 molecules extra have come in or 1 or 2 molecules extra have gone out, then that doesn't really change the mass altogether, right? The mass almost stays the same. I'll give you an example. Let's say we are taking density. All right. So density, we discussed in the first video, density is nothing but mass upon volume. So now let's say I'm taking a very small control volume, Remember, this is my control volume. So now my flow is taking place. All right. My flow is taking place. And because of this flow, a few molecules, they are coming inside my control volume and then going out. All right. So now let's assume that mass of each molecule is m. Mass of each molecule is m. All right. So if there are 2 molecules inside, then my density is going to be 2m upon v, where v is the volume of the control volume. All right. And since this v is going to be fixed, this v is not changed. This v is not going to change because it's a control volume approach. So rho is going to be equal to 2m by v if there are 2 molecules. Let's say if all of a sudden, because of some reason, 1 more molecule has come in. All right. So now the density is going to be 3m by v. So this difference has come in the density. Let's say if by chance 2 molecules have gone out, just 1 molecule is there in the system. Then we have rho equals to m by v. So there's a difference. All right, there's a difference. Why there's a difference? Because there are a very small number of molecules. Therefore, the change in 1 or 2 molecules, it causes a lot of difference, a lot of disturbance in the system. So if we observe density for such a small, if we observe it for such a small control volume, then you will observe that density will keep on varying, because obviously the number of molecules are going to change. So it will fluctuate. It is going to fluctuate throughout. All right. So what we do in that case, we take a very large, or not very large, but we take a large enough control volume. All right. We take a large enough control volume. So if we take a large enough control volume, so let's say there are 10,000 molecules inside this. All right. Let's say there are 10,000 molecules inside this. All right. So what is the mass inside this? The mass inside this is going to be 10,000 m. So the density at this point of time is going to be 10,000 m upon v. Correct? It's going to be 10,000 m upon v. Now let's say if there is a change in 1 or 2 molecules. So let's say 2 molecules extra come in. So the density is going to be 10,002. Oh, sorry. 10,002 m, right? 10,002 m upon v, right? Now, if you observe this difference and this difference, which one is going to be more effective or more noticeable? Obviously, the above difference, 2m and 3m, right? It's going to be more visible. Although the difference is same, two molecules, just two molecules have been changed, or in this case, it's just one molecule that has changed. But still, this difference would cause more variation in the density than this difference. The reason behind this is that when we take a very large control volume, when there are so many molecules in that control volume, that variation of one or two molecules, or even of 50-60 molecules, it won't really affect the overall property that as such, right? That is why the control volume approach, it reduces to a control mass approach, unless and until there is a a different kind of flow, an unsteady state flow, where there is accumulation. Molecules, they keep on getting accumulated. That's unsteady state flow. So in that case, if molecules are just getting accumulated inside, then in that case it would be a different story. But if it's a steady state flow where molecules are constantly coming in and going out without getting accumulated inside, so that in that case you'll not really find too much difference in the property. So that this fluctuation that was coming because of a small control volume, this problem, it goes off. All right. So that's the control volume and control mass approach. All right. Now we finally come to basic material balance equations. So whenever we take a control volume, let's say this is my control volume, then something will be coming inside it, something will be going out of it, something might get stored in it, something might get generated inside this, and something might get consumed inside this. All right. Something might get generated, something might get consumed. So keeping all these things in mind, when we form a basic material balance equation or a basic mass balance equation, general mass balance equation, so that's going to be mass input minus mass output minus mass consumed plus mass generated is equal to mass stored. All right, mass stored. I'll give you a very simple example. Let's say if I have this as my control volume and I'm having A and some amount of B. All right, I'm having A and some amount of B inside. All right, B that is going inside, and outside you get A and B. But let's say the amount here is A1 and B1, and here let's say it is A2 and B2, amounts of A and B. All right, and let's say inside there is chemical reaction which converts A to B, and there is, let's say, another chemical reaction which converts B to C. So we'll get C here as well. All right, we'll get C here in the output as well. So let's say these two chemical reactions are taking place inside. All right, so whenever we are going to do mass balance for A, all right, or let's say, let's be more accurate, let's do mass balance for B. All right, so B that is entering is B1. All right, B that is entering is B1. Because of A in the input, some of B would also be produced. So that is going to be B that is produced. All right, some of this B is going to be consumed. So that is B that has been consumed. And after all this, the remaining B, it is going to come out. All right, it might be possible that some B has been stored here. All right, some B has been stored here. So this is the equation that is going to be formed. So we'll get B input plus B generated is equal to B consumed plus B output plus B stored, right? So this is the general mass balance equation. General mass balance equation. You should all know this equation. And when we go on to energy balance, the same equation is followed there as well. Energy input minus energy output minus energy consumed plus energy generated is equal to energy stored. The same equation is followed for energy balance. So you have to keep this equation in mind. All right. You have to keep this equation. You have to understand this logically. All right. So all the mass that is added to a control volume, it is either accumulated inside or consumed inside, which might also lead to some mass generation, and whatever is left, it would come out as output. All right. So when we go for special cases of mass balance, all right, when we go for special cases of mass balance, then the first case is that there is no chemical reactions. If there is no chemical reaction, then there is going to be no generation, no consumption. All right. Since there is going to be no generation and consumption, therefore, these two terms are going to be zero. All right. These two terms are going to be zero. When these two terms are going to be zero, then you'll simply get input minus output is equal to stored. All right. Second is steady state operation. At steady state operation, no mass is accumulated. Mass accumulated means change in mass with respect to time at a particular point. And as we discussed, for steady state, dm by dt or d property by dt is equal to 0. Right? So it's going to be 0. So that is why if no mass is stored, then this term becomes 0 and the equation becomes mass input minus mass output is the plus generation is equal to consumption. All right. And finally, if there is steady state operation without chemical reactions, this was with chemical reactions. I discussed case 3 with you all. All right. Now, if there is no chemical reaction as well, so even generation and consumption term are going to be 0. Therefore, what we'll get is input equal to output. All right. Input is equal to output. So most generally, we are going to deal with these two equations. All right. This equation, input equals to output, is going to be used for mass balance or material balance without chemical reactions. And the second equation, that is input minus output plus generation equals to consumption. This is going to be useful when we are going to deal with mass balance involving chemical reactions. All right. So whenever we are solving a mass balance problem, there are a few steps that you need to follow. The first step is that you need to draw block diagram. You need to understand the problem, read the problem, and draw a block diagram mentioning all the units that are involved. Second, whatever information has been provided about input, output, composition, mass flow rate, mole flow rate, everything has to be mentioned. Third, set a suitable reference or set a suitable basis for your calculation. All right. So for example, if there are A and B inside, or A and B are going inside, or let's say, let's not complicate it. Just let's say that something is going inside. All right. So we can, for our reference, we can say that this, whatever is going inside is 100 kilomole. All right. This is 100 kilomole. So based on this 100 kilomole, we are going to do our calculations. All right. So we are going to set a reference for our calculations. Then we are going to do a mass balance for different components as well as overall balance for the system. And finally, make equations equal to the number of unknowns and finally solve these equations. You'll understand more when we solve a problem. So let's go to problems. But before that, let's form the mass balance equations. So it's actually quite similar as what we discussed before. Select the control volume that you need to perform the balance on, then form the overall material balance equations for entire input, output stream, irrespective of their individual compositions. All right. So this means that if suppose this is your unit, this is your input, and it's going out. All right, it's going out, let's say output 1 and output 2. All right, so no matter how much of a component is present in input stream and output stream, you are going to make the overall equation, that is input is equal to output. This first overall balance equation you are going to make, and the second equation is based on component balance. All right, you'll get a more clear idea when we solve a problem. So let's solve this particular problem. Make sure that you're very clear with what we are doing for these problems, so that when from the next video onwards, when we'll be dealing with typical mass balance unit operations, there you are not confused. All right, so let's see this problem. A mixture of A and B with 40% A is fed to a separator. Remember, whenever we have a unit, then whatever is added to it. So let's say this block is my unit. So this block, since we are drawing the block diagrams, all the units are within the blocks. So this block is my unit. So whatever is added, this is general nomenclature that you should know. Whatever is added to it, it is known as feed. All right, it is known as feed. So this is my feed and this is usually product. All right, what this usually means is product. All right, so we'll be solving this problem. So a mixture of A and B with 40% A is fed to a separator at the rate of 2000 kg per hour. The separator separates this mixture into two streams, one moving out from the top with 75% A and the other moving out from the bottom with 10% A. Calculate the mass flow rates of the two streams. So as we discussed, the first step is to draw a block diagram. So we are going to draw a block diagram. So in the block diagram, we only have one unit, that is a separator. All right. Then, so this is my separator. Then we have identified the streams. There are three streams. One is the feed stream that is coming inside. So this is my feed stream. Then there are two more streams. One is moving out from the top and one is moving out from the bottom. All right. So this is my basic block diagram. Now I'm going to put in all the information that I have. So what is the feed rate? Feed mass flow rate, that is 2000 kg per hour. So it is being fed at 2000 kg per hour. So since this is feed, this is taken as F. All right, this is taken as F. And the mole fraction or mass fraction, in this case it's mass fraction. So the mass fraction of a particular component is taken as XF. All right, so XF is given to be 0.4. But remember, if we are taking the weight fraction or mass fraction of one particular component, then we are going to take the mass fraction of that component throughout. So for example, here we have taken mass fraction of A for XF. So while we are mentioning using X over here as well as over here, so that means we are talking about mass fraction of A only, right? We are not talking about mass fraction of B. All right, for mass fraction of B, we are going to use X dash or something else, some other term, not X. All right, so XF is 0.4. Then the separator separates this mixture into two streams, one from the top. So let's call the top stream as T, just like we have called this feed stream as F, top stream, let's call it T. And the bottom stream, let's call it as B. All right, so XT and XB are going to be the weight fraction of A in the top stream, and XB is going to be weight fraction of B in the bottom stream. Weight fraction of A in the bottom stream. All right, let's not call it as B, otherwise you might get confused. Just a minute. I'll call it as D, downstream. So let's call it as D, and XD is going to be mole fraction of A or weight fraction of A in the downstream. All right. So the weight fraction of A in the top stream is 75%, so that's 0.75. And weight fraction in the bottom stream is 10, so 0.1. All right, so this is my basic block diagram. I have given every information that is mentioned. So that's all. All right, that is my step number 1. Next, what I need to do is form overall material balance. So in overall material balance, just forget that anything with X is mentioned. Just forget that this or this is mentioned. Just see what else is mentioned. So we have F, we have T, we have D. All right, we have F, T, and D. So whatever, exactly whatever is coming inside, it has to go out. All right, at steady state, right? So whatever is coming inside, so F is coming inside, it has to go out. So that out is basically T plus D. So this is the first equation that you'll make, which is the overall material balance. So since F is 2000, so therefore we have T plus D is equal to 2000 kg per hour. That is my equation number 1. This equation is for overall material balance. All right. Then next we are going to do component balance. Okay. So there are two components, component A and component B. All right. So we are going to make equations for both. So if 0.4 is the weight fraction of A in the feed, then what is going to be the component or what is going to be the amount of A in the feed? It's going to be XF into F, right? What is going to be A in the top stream? So it's going to be XT into T. And similarly, what is going to be A in the bottom stream? It's going to be XD into D. All right. So since we have XFF, XTT, we have XT and we have XT. So the equation becomes 0.75T plus 0.1D is equal to 0.4 into 2000. That is your equation number 2. So basically we have two variables T and D and we have got two equations. So we can solve the problem, but just for the sake of understanding, I'm going to make equation for B as well. So what is the mass fraction of B in feed? If it's for A, it's XF, then for B, it's going to be 1 minus XF. So 1 minus XF into F is equal to 1 minus XT into T plus 1 minus XD into D. Mass fraction of B in the top stream into the top stream plus mass fraction of B in the bottom stream into mass flow rate of the bottom stream. All right. So that is equal to, what is 1 minus XF? 0.6 into F, that is 2000, is equal to 1 minus XT, that is 0.25, T plus 1 minus XD, that is 0.9 B, equation number 3. So let's say if this F feed wouldn't have been known, then we could have solved these three equations altogether and got the result. All right. But for now, since only two of them are unknown, so we can use any of these two. We can use a combination of any of these three equations and solve this problem. So let's say we are using equation number 1 and equation number 2 to solve this particular problem. So we are going to get T and D as top stream. We are going to get as 923.07 kg per hour. And bottom stream that we are going to get is 1076.93 kg per hour. And if you want, you can check this by adding these two. It should result in 2000 kg per hour. All right. So this is basically your material balance. This is how you do material balance. All right. So next, hope you are clear with example number 1, and then we'll move on to example number 2. Example number 2 states that there are two salt solutions which are stored separately. 400 kg solution contains 20% salt and 600 kg solution contains 55% salt. What is the total mass and composition of the solution obtained by mixing the two? I want all of you to pause the video and try making the block diagram, only the block diagram yourself. Go ahead, pause the video and make the block diagram yourself. So hope you have made the block diagram yourself. So let's see how the block diagram is going to look. Two salt solutions are stored separately. The 400 kg solution contains 20% and 600 kg solution contains 55% salt. Total mass of the mass and composition by mixing the two. So our unit is basically the mixer. All right, you don't need to write the name of the unit, just let's call it unit. All right, since you have not understood what the different unit operations are yet, so that is why let's not write the unit name for now. Let's call it unit. All right, now this unit has first had one solution and the second solution. So solution number 1 and solution number 2, and they have been mixed, and a single stream, a single solution has come out. All right, so this is my block diagram which shows that two solutions have come in and one solution has fallen. So let's call the solutions that have come in as S1, S2, the mole fraction here being x1, or mass fraction being x1 and x2, and let's call this as S and the mass fraction of salt as x. All right. So we have 400 kg solution. So the first one is 400 kg solution, and the mass fraction is 0.2. 20% is 0.2. All right. Then the second solution is 600 kg. So S2 is going to be 600 kg. Then X2 they have given to be 55%. So that is 0.55. What is the total mass and composition of the solution? So we don't know S or X. We don't know any of them. So now the next step, you have to form the overall material balance equation. Pause the video and form the equation yourself before I form it for you. So when you form the material balance equation, the overall material balance equation, so the overall material balance equation is going to be S1 input stream number 1 plus S2 input stream number 2 is going to be S, right? That is what you're going to do. S1 plus S2 is equal to S, right? So S1 is 400, S2 is 600. So S is equal to 400 plus 600. So from the first equation itself, we have got S, which is 1000 kg. So there are certain questions where you might get from the first equation itself, you might get one of the variables. So that means the second equation that you're going to form, you're going to substitute that variable in that equation and then solve for the remaining variables. All right. So we have got S as 1000 kg from this. All right. Now go ahead, pause the video and form the component balance equation. So when we form the component balance equation, the common component balance equation, so we are going to balance salt, right? So we are going to balance salt. So it's going to be x1 s1 plus x2 s2 is equal to xs. All right. Now x1 we know as 0.2, s1 is 400, x2 we know as 0.55, s2 is 600, x we don't know, and s is 1000. Hope you people could form this equation. And I'm also hoping that you would have calculated x from this equation. So you get 0.2 into 400 plus 0.55 into 600 whole upon 1000, right? Whole upon 1000. So when you do that, you'll get x is equal to 0.41. Hopefully you people could get this value. If not, then please go back in this video and try to understand how to form these equations and how to get the value. All right, fine. Then we move out to the next example, that is example number 3. Now, example number 3 is more important for you all because this consists of more than one unit. So for now, till now, what we have done, we have taken just one unit and we have done our solving. So for example, here we have taken separator, just one unit, and we have solved. Similarly, over here, we have just taken one unit, that is the mixer, and we have solved. Now, we are going to take more than one unit. So for solving material balance equations for more than one unit, there are different methods that are involved. So I'll discuss each of them with you all. But first of all, let's understand what the problem is, and then let's draw the block diagram. All right. So pure water is passed through a mixing unit at the rate of 5000 kg per hour. All right. So my first unit that I have identified is a mixing unit. So again, I'm not going to write the name of the unit. I'll simply write unit number 1 in which pure water is passed. All right. So pure water, let's call it W. So W is equal to 5000 kg per hour. All right. Then where it is mixed with methanol coming in at 400 kg per hour. So over here you have methanol that is coming in at 400 kg per hour. All right. So it's methanol. So let's call it as M. All right. Then the mixture is then passed through another unit where it is mixed with ethanol. So now whatever the mixture you have got from here, it is passed into another unit. Again, I'm not going to name the unit. I'm just going to call it unit 2. All right. So this mixture, this is the mixture. All right. This mixture has gone into unit number 2. And in the unit number 2, you have ethanol coming in. So I'll call it as E. All right. So ethanol coming in is at 600 kg per hour. All right. Then this mixture is finally passed through a separator to get methanol water containing no ethanol. Let's back up a bit. This mixture is finally passed through a separator. So from here, whatever mixture we get, so let's call it as mix 1 and call this one as mix 2. All right, so whatever mix 2 we are going to get, this is passed through. Again, I'm not going to name the unit. I'm just going to say unit 3. All right. So this mixture, it is passed through a separator, that is unit number 3, through a separator to get methanol water and ethanol water. So methanol water is pure methanol. It does not contain ethanol. And similarly, ethanol water is pure ethanol, no methanol. All right. So here we get methanol water. So I'll call it as M1. And here we get ethanol water. I'll call it as E1. All right. And then it is said that the output rate of methanol water mixture, that is M1, is 3100 kg per hour. So please make sure that you people have understood how to form this block diagram. If you people could not understand, rewind and again watch this part, how I have made this block diagram. If you have not made the block diagram yet, then please pause the video and make the block diagram first. After that, we'll continue with our solving. So now, hope you have all made this block diagram. Now, whenever we are dealing with more than one units, then there are different methods of solving these problems. All right. So let's not go into different methods. Let's just see how many different equations you can make. All right. So first way of making equations is doing material balance about each unit. That is unit number 1, unit number 2, and unit number 3. So if you have n units, you are going to get n equations around each unit. All right. So you are going to do overall material balance about each unit. You can do component balance about each unit. All right. That is one form of equations that you can get. All right. One more form or one more way in which you can solve these equations or you can make equations is by making a system boundary. Making a system boundary. This is known as the method of system boundary. So what I'm going to do is I'm going to make a system boundary about this entire system. All right, I'm going to make a system boundary about this entire system. All right, so this green is basically my system boundary, or you can say this green colored box is my control volume. I have taken this as my control volume. All right, now about this green control volume, I'm going to do my material balance. So what I'm going to take this green control volume as my only unit. This green, this entire system, it reduces to a green system which has only one unit. All right, which has only one unit. So from this diagram, just see whatever is coming inside this green unit and whatever is going out of this green unit. So you can clearly see that from here we have W that is coming in, right? From here we have M that is coming in. From here we have E that is coming in. From here we have M1 going out, and from here we have M2 going. All right, I'm not going to consider anything else that is within this green box. All right, within this green box, I'm not going to consider anything. All right, so assume that all the other things inside this are no more. All right, only whatever is going out and coming in overall, this inside this green box is going to be counted. So we have not taken M mix 1 and mix 2 because mix 1 and mix 2 are basically inter-unit transfer, right? From unit 1 to unit 2 and unit 2 to unit 3, right? It is not a transfer from surroundings to the system or surroundings to the unit. Like water, it has been transferred from surrounding to the unit 1. Methanol surrounding to unit number 1. Ethanol surrounding to unit 2. Methanol unit 3 to surrounding M1, and even unit 3 to surrounding. But mixed 1 has been transferred from unit 1 to unit 2, and mixed 2 has been transferred from unit 2 to unit 3. That is why we are not going to take these while we are making the block diagram for the green unit. All right. So once we have made the block diagram for green unit, we can make material balance equation for green unit itself. Okay, to ease our problem. All right, to make our problem very easy, what we can do, we can simply make a material balance equation about this unit. All right, so the material balance equation for the green unit is going to be W input plus M input plus E input is equal to M1 plus E1, right? Now we have M1, we have W, we have M, we have E. So this E1 is going to be W, that is 5,000, plus M, that is 600, sorry, 400, plus E, that is 600, minus M1, that is 3,100, right? This M1 has come here. So minus 3,100. So this is 6,000 minus 3,100, 2,900 kg per hour. That is E1. All right, that is E1. Hope you people have understood how we got E1. We have done overall material balance about the green unit. All right. Then we are going to do component balance about this green unit. All right. Component balance about this green unit. So component is basically your methanol, methanol and ethanol, because here we have mixtures. So we have ethanol and methanol as two different components. So we are going to first of all balance methanol. All right, because M1 and E1 are basically methanol and ethanol mixtures. Therefore, our components include methanol and ethanol. So let's say XM is the is the mass fraction of methanol in M1, and XE, let's say, is the mass fraction of ethanol in E1. All right, I've written M2 over here. I'm so sorry. Just a minute. It's E1. All right. Okay. So now when we are going to do component balance about methanol, so let me first of all mention XM and XE. All right. So when we are going to do the component balance, so methanol coming in is only M. So that is M, right? Incoming methanol is only M, right? Outgoing methanol is XM into M1, right? It's XM into M1 because methanol is coming in as pure methanol, but it is going out as a solution of water, right? Forming a solution with water, right? That is why we have M equals to XM into M1, all right? Because the mass fraction of methanol in M here, mass fraction of methanol here is 1, right? So if we do mass fraction of methanol into M, so that is going to be M only. So we will simply get M equals to XM into M1. So from here, you'll get XM is equal to M upon M1. So M is 400, right? And M1 is 3,100. So you'll get 400 upon 3,100. That is equal to 0.129. All right. Then the next balance that you're going to do is for ethanol. All right, for ethanol. So when we are doing ethanol balance, then again, incoming ethanol is only E. Incoming ethanol is only E, right? Pure ethanol. Outgoing ethanol is XE into E1. Therefore, we get XE is equal to E upon E1. That is, E is given to be 600 and E1 is, we calculated 2,900. So it's 600 upon 2,900. That is 0.207. All right. So hope you people have understood what I have done here. I took all the units within one system boundary, which I called it as my control volume. All right. Then I saw that what all has been transferred from the surroundings to this system or from this system to surroundings. That is, I eliminated all the inter-unit transfer, right? From unit to unit. I eliminated all that. And finally, I made my new block diagram. And based on that new block diagram, I made my overall material balance and component balance equations, right? Now, because of ease in the problem, because of simplicity of the problem, I have been able to solve these equations using simply this block diagram, this green block diagram. But at times what happens, the questions are complicated, where you're not able to simply use the green block diagram. So for example, I ask you that what is the composition of ethane and methane here in mix 2. So let's say if I am asking this, So you'll not be able to tell anything based on this block diagram, because we have nothing over here, right? We have nothing. We don't have mix 2 over here. So in that case, what we do is we form equations for individual units. All right, we form equations for individual units. So what we are going to do, we are going to draw 3, because we have 3 units. So we are going to draw 3 different block diagrams. One block diagram for unit number 1, one block diagram for unit number 2, and one block diagram for unit number 3. Since there are 3 units, so 3 individual block diagrams. So when we do it for unit number 1, we get W, M, and mix 1. W, M, and let's not call it mix 1. Let's call it P1. All right. So the mix 1 is nothing but P1, and mix 2 is nothing but P2. All right. Then for unit 2, I have P1 that is coming in. So P1, I have E, and I have P2 that is going out. So P2. And finally, I'm going to make a block diagram for unit number 3, where P2 is coming in and M1 and E1 are going out. So P2 is coming in and M1 and E1 are going out. All right. Then, all right. So once we are done with this thing, once we have drawn the block diagrams, let's give more information. So we know W and M. W is pure water, M is pure methanol. But P1 is a mixture of methanol and water. So let's call it X1. All right, let's call it X1. So actually, let's call it as XM1, right? XM1, because it's mole fraction of methanol, right? Then P1 again over here, I'll have XM1. E is pure ethanol. Now P2 will contain both methanol as well as ethanol. So it's going to be XM2, which is mass fraction of methanol in product 2, and XE2, that is mass fraction of ethanol in P2. All right. So in this block diagram, when we come back, so we'll have XM2 and XE2. And then again, over here, it's pure methanol without anything. So it's XM, and over here we have XE. All right. So this is what we have. All right. From the previous problem, we have already calculated XM and XE as 0.129 and 0.207. So XM I have calculated as 0.129 and XE I have calculated as 0.20. All right. Then we also have E1, we have M1, we have W, we have M, we have E. All right. So let me just mention all these values. This is 5,000. This was 400. Then this was 600. This was 3,100. And this was 2,900. Right? Even was 2,900. So these are the values. So these are my 3 block diagrams complete. All right. Now what I'm going to do, for individual block diagrams, I'm going to make individual equations to get my results. So for block diagram number 1, I'm going to make an equation for overall material balance. So overall material balance gives me W is equal to M plus P1. I'm so sorry. Input is equal to output. So it's going to be W plus M, because both of them are coming in. So I'll get W plus M is equal to P1. Input is equal to output. All right. So W is 5,000, M is 400. So it becomes 5,400 is equal to P1. All right. So P1 is 5,400 kg per hour. Then the next equation that I'm going to make is for component balance. So component over here, I'm going to take methanol. All right, so I'm going to balance methanol. All right, so I'm going to balance methanol. So methanol balance gives me incoming methanol, that is only 400, is equal to outgoing methanol, that is xm1 into p1, right? So xm1 is going to be 400 upon p1, that is 400 upon 5400. All right. So when we do the calculation, 400 upon 5400, that is going to give us 0.074. That is my xm1. All right. So from the first block diagram, I have got xm1. Then from the second block diagram, I'm going to make overall material balance equation. So that is going to be P1 plus E. P1 and E, they are both incoming, and P2 is going out. So it's going to be 5400 plus E is 600. Therefore, P2 you will get 5400 plus 600, which is 6000. All right. Then I'm going to do component balance. So now there are two components here. First component is methanol. So when we do methanol balance, that is going to be xm1 p1 is equal to xm2 p2, right? So xm1 is 0.074, p1 is 5400, and p2 is 6000. All right. So from here you get xm2 is equal to 0.067. All right. Then you are going to do ethanol balance. So ethanol balance is going to be equal to ethanol that is coming in, that is E, and ethanol in P2, that is XE2 into P2. So XE2 is going to be E upon P2, that is 600 upon 6000, that is 0.1. So XE2 is 0.1. So we come to the third block diagram. XE2 is 0.1, XM2 is 0.067, and P2 is equal to 6000. Now XM and XE we have already calculated from previous green block diagram, but if let's say we wouldn't have calculated, then we would have used the same material component balance over here. We would have balanced methanol. So for methanol, we would have done xm2 into p2 is equal to xm into m1. And for ethanol, we would have made the equation xe2 into p2 is equal to xe into e1. So hope you people have been able to understand how do we deal with multiple units. More importantly, hope you people have been able to understand how to form different material balance equations, which includes overall material balance as well as component balance equation. My overall material balance equation, you just have to see input stream, output stream. When we form component balance equation, we multiply the input stream by the mole fraction or mass fraction of that component. All right.